Topic 8. What I want to look at in topic 8 is percentage composition, determining the empirical formula and determining the molecular formula. Imagine yourself as a mining engineer. You want to weigh up the pros and cons of extracting, let's say, iron from one of two sites. The iron ore of the two sites might be a different chemical. You want to know how much of that material, that dirt that you dig out of the ground, contains iron. One site's probably going to be more economic than the other because maybe one of the factors is that it has a higher mass of iron in the ore than in another occasion. Imagine yourself perhaps as a pharmacist. A patient presents with anemia. You need to advise them on an iron supplement. Which one you might advise them on might depend on the amount of iron they need. And so you need to know something about the amount of iron in a selection of compounds available to you in order to advise your client. So, first thing I want to look at is looking at the percentage composition by mass of various elements within a compound. And to do this, let's use glucose as an example. Happens to have that formula. So one molecule of glucose contains 6 atoms of carbon, 12 of hydrogen and 6 of oxygen. From what we've seen this morning, 1 mole of glucose contains 6 moles of carbon, 12 moles of hydrogen atoms and 6 moles of oxygen atoms. So from the formula we can determine that. We can determine the mass of 1 mole of glucose. The mass of 1 mole is going to be the sum of the various molar masses of the component parts. If I look up the periodic table, its carbon weighs in at a molar mass of 12.01. 6 of those plus 12 of hydrogen at 1.01 plus 6 oxygen atoms at 16 gives me a total molar mass, in this case, of 180.18 grams. So, 1 mole of glucose then has a mass of just over 180 grams. And this contains in terms of carbon, six times the molar mass of carbon as the mass of carbon. It contains 12 times 1.01 grams of hydrogen and 6 times 16 grams of oxygen. And if I work that out, I end up with these figures, which of course add up to 180.18 grams. But what I can now do, knowing this, is say that for carbon, I have a total of 72.06 grams of carbon in 1 mole of glucose. And if I was to convert this to a percentage, I can determine that the percentage of carbon by mass in glucose works out 40%. And similarly, for hydrogen, I can determine that the mass of hydrogen in 1 mole is just over 12 grams. The mass of 1 mole is just over 180 grams. So converting that to a percentage, I find I get a percentage hydrogen 6.7% by mass. And again, this highlights the fact that from the molecular formula, I've got more hydrogen atoms than either of the other two types of atoms. And yet, the amount it contributes to the overall mass of the compound is very small by comparison. And you can do the same thing for oxygen. And we end up with a percentage for oxygen that works out to be 53.3%. Hopefully that adds up to 100, yes. And we can then say that glucose contains just over half its mass in oxygen, 40% in carbon, and a fairly small amount in hydrogen. Let me do another example along the same lines, and this is perhaps back to imagining yourself as a mining engineer. Let's say we have an iron sulfide compound that you've analysed in the lab. Let's try this type of problem from the other way around. You've analysed this sample in the lab. You find that by mass, your iron ore returns 63.5% of iron, and sulfur turns in at 36.5%. What you want to do is determine what type of ore you've got, determine the formula of this compound. Now, the first thing you do is just check that with an experimental error, these figures add up to 100%, and I'll show you later on what we do when it doesn't add up to 100%, and sure enough, it does. And the way that I think about this is in terms of 100 grams. And that's convenient because we're looking at a percentage. So imagine that we have 100 grams of this iron ore. Within that, we have 63.5 grams of iron. And similarly, in 100 grams, we have 36.5 grams of sulfur. But we know that the formula of a compound depends on the ratio of atoms, not on the mass of atoms, the ratio of numbers. So my first stage is to convert these masses into numbers of moles. And a recap of that really important formula, the numbers of moles, or the amount, is the mass in grams divided by the molar mass of the material, which we look up on the periodic table in grams per mole. I've used a slightly mathematical way of expressing something as a quantity per something else. Kilometres per hour, number of distance you go divided by the time travelled. Grams per mole, mathematically expressed, is moles to the minus 1. Okay, so we have that number of grams. The amount of iron, or the number of moles of iron in 100 grams, is going to be 63.5 divided by the molar mass of iron. We need to look this up on the periodic table. The molar mass of iron is 55.85. If I do this calculation, I find that it works out that I got 1.14 moles of iron in my 100 gram sample. Similarly, for the sulfur, imagine we've got 100 grams, 36.5% of that is sulfur, so equivalent to 36.5 grams of the material is sulfur. The amount and the number of moles we have of sulfur is the mass divided by the molar mass of sulfur, and that also turns out to be 1.14 moles. What I then do is compare my numbers of moles of the two components. I see they're the same in this case. Well, we don't write the formula as Fe 1.14 sulfur 1.14. Convention has it that we express the formula as the lowest integer ratio of the atoms. 1-to-1 molar ratio, I can express the formula then just as FeS for iron sulfide. So, two ways of doing the calculation. Starting with a known formula, we can work out the mass of the component parts, or by analysis, we can use the information to determine the formula of the compound, and the formula we get is actually an empirical formula. I'll show you a case a little later on where it's not an empirical formula. Okay, let's look at another couple of scenarios. And the first one I want to look at is another sort of analysis type question. And imagine we have an analysis where nitrogen returns a value of 26.2% as a mass percentage. Analysis of my compound gives me an analysis for chlorine at 66.4%, and of hydrogen turns out to be 7.5%. Now, what I want to do is now convert this into a formula of a compound, an empirical formula. First thing I check, do they add up to 100%? And yes, they do, pretty much with an experimental error. And I can imagine that in 100 grams, I'm going to have 26.2 grams of nitrogen, 66.4 grams of chlorine, and 7.5 grams of hydrogen. If I now think of the molar mass of these components, nitrogen has a molar mass. And now I've got to think a little bit more carefully. Molar mass of 14 or 14.01. Why do I think carefully? Well, I know that nitrogen as a element always goes about as in the N2 molecule. And so if I wanted to look at the mass of a mole of nitrogen gas, I'd have to say, okay, it's going to be 28.02. But I haven't got nitrogen gas here. I'm looking just at nitrogen atoms within this compound. So the molar mass that I use is that for the atom, 14.01. Chlorine, 35.45 molar mass of chlorine, and hydrogen, 1.01 is the molar mass of hydrogen. If I now, and I'm sort of tabulating this, which sometimes is an easy way to do it, and I'll use tabulation quite a lot in the next topic. If I divide the mass by the molar mass, I will get the number of moles. So in 100 grams of this compound, mass divided by the molar mass gives me the number of moles, and in the case of nitrogen, it's 1.87. In the case of chlorine, mass divided by molar mass gives me the number of moles, which again is 1.87, and then if I divide 7.5 by 1.01, I get a number of moles of hydrogen in my 100 gram sample of 7.4. Now, in a previous example of iron sulfide, it was easy to see that we had a 1-to-1 ratio of iron atoms to sulfur atoms. It's not so obvious here. We need to find the lowest integer ratio. And in almost all cases, the way to start this is by dividing all the numbers of moles by the smallest molar figure. So, if in my next row I have a ratio of moles, I'm going to try dividing through by 1.87. And when I do that, of course, those first two come out to be unity. And if I divide 7.4 by 1.87, then that comes out to be 4. Don't have the exact figure, but it comes out to be pretty close to 4. There might be a bit of experimental error here, so don't expect absolutely spot on integer values. What I can now say is a mole ratio 1-to-1 to 4 gives me a formula of NClH4 for my compound. And that will be correct. And then I can, with those atoms, perhaps start playing around to see if I can get a structural formula. Put the atoms together in a way that the bonding gives us a reasonable result. In all cases, we've determined the empirical formula, the lowest ratio of atoms. This type of analysis can't give us the molecular formula. We need additional data. And what I'd like to just show you is a couple of pictures of the machines that we use to actually get some of this data. This type of analysis is particularly common for compounds which involve carbon, hydrogen, nitrogen and oxygen, for organic compounds. Of course, in the old days it was very careful measurements and long, laborious analysis. Nowadays the analysis is done by a machine, and all you have to do is weigh in the sample and the computer does the rest. For organic compounds, and I'll give you an example of those, one of those in one moment, carbon and hydrogen are always present, and nitrogen is quite often present, but then so is oxygen. And we have a little bit of a problem with this analysis in that it is a combustion analysis. It burns the sample and then determines the amount of carbon dioxide or water or nitrogen given off, and that actually enables us to determine the amount of carbon, percentage carbon, percentage hydrogen, percentage nitrogen, but we cannot determine the percentage of oxygen present because the sample is always burnt in an oxygen atmosphere. But that would still only give us the empirical formula. We need a way of weighing the molecules. And this is done by a mass spectrometer, and this old picture indicates the sort of size that the first mass spectrometers were. They were people size. They are machines that literally weigh molecules one at a time. They used to be very large, but now they are effectively a desktop size machine. The way it works is the sample is injected into the machine. There is a beam of electrons which we say ionizes the sample. It converts it into cations by removing an electron, and we have now got a charged beam of particles. a charged beam of molecules. They can be separated by passing them through a magnet. Imagine a charged particle. It's accelerated into the machine. If it's a very heavy particle, it will keep lumbering on more or less in a straight line, even when it goes into the magnetic field. If it's a very light particle, it's going to be influenced greatly by the magnetic field and curved around a particular pathway. So, the combination of charged particles and a magnet enables us to determine the mass of the particles. We have a detector the other side that has a recorder attached. A mass spectrum of a compound might look like something like this, and we can get information about the makeup of the molecule as well as its molar mass. Just want to introduce you to Auntie Jen. She actually operates mass spectrometer at the National Measurements Institute, where I've got a collaborator. This was bought for the 2000 Olympics, so it's a little bit old now, but you can see the components. The sample goes in at this end, and in terms of the use of it in the Olympics, we have a collaboration looking at doping in athletes, and we collect a lot of urine actually as a result of competition. The lab calls it liquid gold, and what happens is it's injected into the machine, and this is an ion beam that ionizes it. The molecules pass into a magnetic area and so into a detector, and it separates all the component parts into the various constituents so that we can see whether there is an abnormal level of a steroid or a diuretic or one of the other banned substances in the urine that's put into the mass spectrometer. Okay, well, back to the blackboard and some examples. The last example I want to do with you is a slightly more complicated one. The scenario is that an analysis gives us a percentage mass of carbon of 40%. And this is example 3 on page 4. It gives us hydrogen at 6.7%. And that's all it gives us. So instantly we see that this doesn't add up to 100%. We assume that the missing element is always oxygen, and that's a fair bet. So we can say by difference, oxygen is 100 minus 46.7, which gives us 53.3. I can therefore say that in 100 grams I have 40 grams of carbon, 6.7 grams of hydrogen, 53.3 grams of oxygen in this compound. The molar mass is something I look up from the periodic table. For carbon, 12.01. For hydrogen, 1.01. For oxygen, 16.00. If I divide mass by molar mass, I get numbers of moles. So the number of moles of each of these types of element in my 100 gram sample works out to be 3.33 moles of carbon, 6.6 moles of hydrogen, and 3.33 moles of oxygen. What I can do is look at the ratio of moles by dividing through by the smallest of these figures. And actually by eye, I can see that 6.6 is about twice the size of 3.3. So just by inspection, I can say it's a 1 to 2 to 1 ratio. And so I can determine the empirical formula of this material as CH2O. And I might be able to draw a structure that has that formula. But it's not the whole answer. I'm told in this example that the molar mass of this compound is 120. So, but the molar mass is 120. If I determine how much of a molar mass, how much 1 mole of CH2O would weigh, carbon is, let's use the whole number figures, 12 plus 2 plus 16, so it's 14, 20, 30. 1 mole of CH2O would weigh just 30 grams. I'm told that the molar mass of my compound is 120. That means that 1 mole weighs 120 grams. How can I rationalize the two of these? Well, the molecular formula is going to be a whole number multiple of the empirical formula. The multiple I use is going to be molar mass of the molecular formula, determined experimentally, divided by the molar mass of the empirical formula, which equals 4. In other words, we've used some instrument like the mass spectrometer to determine the molar mass of our molecule. It is 4 times greater than I'd expect from the empirical formula that I have from analysis. So I can say that the molecular formula is going to be 4 times everything that's in the empirical formula. C4H8O4. Okay, so quick recap. This brings together empirical formulas and molecular formulas. Empirical formulas are the lowest ratio of the atoms combined to give that compound. We use them for ionic materials. Molecular formulas, much more focused on molecules, and they are the actual numbers of atoms within the molecule. We can use this sort of calculation to determine the percentage mass of any of the particular constituent elements in our compound. We can do this the other way around, and if analysis gives us a percentage mass, we can use that information to convert it to relative numbers of moles, and so determine a reacting ratio of moles, and hence the formula of the compound. But the formula that we get is an empirical formula. We need a bit of extra information, and that is the molar mass of the compound, in order to convert the empirical formula into a molecular formula, the actual numbers of atoms of each sort within that molecule.